We are happy to have today Emmanuel who will tell us about Legendrian barriers.
Oh, okay, thank you. So thank you for this introduction, for the invitation. Okay, so it's nice to have this opportunity to explain this work. So indeed, okay, I want to apologize already before even the starting for the poor English, and maybe so I will try to. I hope the slides are good enough, but we'll see. So it's not so easy to prepare this Zoom talk. So anyway, so what I want to discuss is about Legendrian barriers, and it starts with Lagrangian barriers. So let me just remind in a few words about Lagrangian barriers. And what I want to emphasize here is that somehow it's so these Lagrangian barriers are effect of Lagrangian rigidity at small scales. Okay, it's a phenomenon that describes small scales Lagrangian rigidity. And okay, so let me state the theorem. So the theorem in this form is due to Biran, Donaldson, and Giroux. So Biran did the Keller case, and then you need this work by Donaldson and Giroux to have a statement in symplectic manifold, in general symplectic manifold. So here M omega will always be integral symplectic manifold, and meaning that the class of omega is in Z, right? So it has only integral periods. And then the statement is that for any k large enough, there exists an isotropic CW complex gamma k, and whose complement is small from symplectic point of view, right? It has many capacities smaller than 1 over k. And okay, so this gamma k I will call, so Biran call them barriers, right? So, and usually they are Lagrangian. So I will not say isotropic, even whether maybe there are subcritical isotropic cells, but I will always say Lagrangian skeleton or Lagrangian barrier, or okay. So these are these gamma k. And when I say that, so that they have many capacities less than 1 over k, there are many of them, but I will focus, what is important for me here is the following two. So first, the ball embedding and the Chilibak-Monkey's Lagrangian capacity. So let me just draw the picture. All right, so you have M omega, and inside this symplectic manifold, what you have is a gamma 1, and then if you, so k, I will say k is the order or the degree of the whatever, right, of the skeleton. And if you take the gamma 2, it will be something like this. And then, okay, gamma 4 will be something which is more complicated and in some sense denser. And here, if I go to gamma 8, I will have something like this. Maybe, by the way, okay. And okay, and maybe one word in particular. I always say the case Lagrangian skeleton. There is no uniqueness, but I will say just to say that it's the case, right? And so this statement is that, so here this is gamma 8. So statement tells that if you try to embed in the complement of a ball, right, in M, but in M minus gamma 8 or gamma k, then this ball has size maximum 1/k. And the second one, so maybe chili-back monkeys. So this is in blue is this ball embedding capacity, and the Lagrangian one is something like this. It says that if you have in the complement of gamma k a Lagrangian submanifold, then it must have a disk. So there is a disk with boundary on the Lagrangian whose area is less than 1/k. Okay. And this for any possible Lagrangian embedding in the complement. Okay.
Is it not for tori, Emmanuel?
Sorry?
Is it not just for tori?
It's not just for tori. I just draw torus, but this can be any Lagrangian embedding.
But the chili-back monkey is for tori, right?
Or yeah, okay. So there is so you have to adapt a little bit the proof, but you can prove that in fact it holds for any Lagrangian embedding.
Okay, thank you.
So yeah, you need a bit of upgrade, but that's fine. Okay. So this is what I will call the phenomenon of Lagrangian barriers, right? So in the gamma k, if you have a larger Lagrangian, in the sense that it has no too small positive disk of area too small, right? Then it has to intersect gamma k, and the same with balls. Okay, so the point is that here so we have a statement that states there exists, and it's always better to have examples, right? There are not so many examples, but there exists some. So first of all, maybe an example of Lagrangian skeleton. The easiest example is in dimension 2. So when you take a dimension 2 a surface, right? If you cut it, okay, but this one will be complicated to cut. But if you cut it enough topologically, so that the only things that remain, so you have to remove the many things, so that everything that remains are disks. So all the disks are disks. Sorry, I should have. I will try to. I'm sorry. Okay, so the skeleton will be in red. So you have to remove enough things so that the complement are disks and of area 1/k. So all these disks have area 1/k. Then the complex, so okay, it's a Lagrangian complex, right? It's a complex of curves. Then this complex of red curves can be made a K skeleton. Okay, so this is one example, and from this you can make products. Okay, so you can okay, so in a disk it will be easier. You can take a product of surfaces, a product of skeleton, and this will be a skeleton. But okay, so this will be skeleton associated to polarization which is singular, not smooth. This matter of polarization will come later on, but just what is important is that this the theorem itself do not apply. So this rigidity at small scale do not apply to this to this kind of Lagrangian skeleton. So sometimes in very specific case, for the moment in dimension 2, we can still have such statements also for this skeleton of singular polarization, but it's complicated. So I don't want to get into this, right? So I will so these ones are not good skeleton in this talk, okay? But still, when you have this Lagrangian this skeleton, which are, what you can do is kind of, so you have this singular polarization, you can smoothen them or desingularize them, and so maybe another two examples. So a product of surface is gives you this. Another example of good skeleton, but unfortunately associated to singular polarization, is the case of the Clifford torus. So you take the Clifford torus in Pn, or the Clifford torus even in the polydisk P2n of 1, or in CPn. Okay, so you take the Clifford torus. They are skeleta of degree d+1 for CPn and of degree 2 for P of 1. Okay, so just recall that these 2 or this d+1 are the K here. And okay, so they are associated to non-smooth polarization. So the theorem does not apply, but as I told, what you can do is smoothen. But then when you smoothen, so for instance, just for how could I? So here it's polarization of degree, for instance, 3, and the polarization is union of hyperplanes here. And when you smoothen, what's going on is that you have to add some cells to this CW complex, right? And so the picture at the end is the following. For these algebraic examples, you can really compute the skeleton, and then you get this Clifford torus together with. So here it's not really a CW complex; it's some more complicated thing, but still above each of these points. Sorry. Yes. So here it's in blue, but it should be in red, right? These are the skeleton, and above all these points. So this is obviously the Delson polytope associated to CPN, right? And therefore, above each point of this polytope, you have a torus, and above, so this skeleton above each point, the skeleton is a linear subtorus of degree n-1, okay, of dimension n-1 inside the fiber torus, and here, okay, you get all these. So here you can really describe the picture, and so the theorem again tells you that yes, that in the complement of these things you cannot find two small Lagrangians. So for instance, obviously for this one, for k is equal to 1/3, what you would like, so it's 1/3, sorry, 1 over d+1. If you try to put Lagrangian of monotone Lagrangian, so the constant of monotonicity in CPn is 1 over n+1. Okay, and you would like to be able to prove that it intersects the Clifford torus itself, right? What you can prove with these things is that it intersects either the Clifford torus or one of these Lagrangian cells. Okay, and the same for the polydisk. Okay, so these are examples. And let me now go to the question of getting contact analog of this kind of statements. And so the point is that we noticed with Felix that in fact this rigidity at scale 1/k show up in a Legendrian in the contact context. So there is a Legendrian CW complex of arcs in S3 with the standard contact form or with the standard contact structure that has this rigidity at scale 1/k. So I will get back to defining precisely what I mean here for this rigidity at scale 1/k. But okay. But then what I mean is that there is this, then once this is known for S3, you can ask whether you have a contact analog of Lagrangian barriers, right? And whether in it, for instance, whether in any contact manifold you have a Legendrian CW complex, or rather a sequence of index by k by the degree, some degree of Legendrian CW complexes whose complements are smaller and smaller in some contact sense. So the point obviously is that in symplectic geometry, having giving a meaning to size is fine. We have these capacities. In contact geometry, it's a bit more complicated, but still there are. You can imagine some examples of measuring, right? So first, if we want to mimic the ball embedding capacity, so we need some rigidity for embedding, and so for instance, we can take the contact balls, right? We can try to probe m minus lambda k by embedding inside the contact ball. So by this I mean B2n of A cross S1, and ask for lambda k to be such that in this complement you cannot put such a contact ball of size larger than, for which A is larger than 1/k. Okay, and another way also to measure maybe a contact manifold would be the following. So what you can try to do in the same as, so in the symplectic case, we try to see Lagrangian in the complement. So the analog will be Legendrian submanifold in m minus lambda k, and disks with boundary on the Lagrangian are replaced by, can be replaced by have the analog as the Reeb chords of length something. Okay, so you can try to say, for instance, that a Legendrian, that maybe in the complement of m minus gamma k, lambda k, sorry, the Legendrian submanifold always have short Reeb chords, but obviously to speak about short Reeb chords, you need to fix, so I don't know exactly, but for instance, a reference contact form, but some notion of size, because obviously what you can do when you have a contact form, you can just shrink it or expand it by constant, and then the length of the chords, of the Reeb chords will be, the Reeb chords will be the same, just their length will be shrinked or okay. Okay. So the answer that I want to propose here is that, in fact, indeed, this S3 case is not an isolated phenomenon, And what I could prove at least was that, so my guess is that it holds for any contact manifold, but I could prove for prequantization. So that's, so maybe just before I get to the statement itself, let me just put the setting, set the notation. So what is prequantization? So I start with an integral symplectic manifold, and now this is N2. Basically, for the main of the talk, of the rest of the talk, it will be this. And then, okay. Yes, I didn't change. So then you can define P of N2 to be the contact manifold obtained from N by considering the S1 bundle with Euler class minus 2. And alpha here is just a connection. So it's an S1 bundle. So if N has dimension 2N, then this is 2N plus 1, right? And you require that that the Euler class is minus 2, and you take alpha, a connection form with curvature plus 2, and then this alpha is a contact. You can check that because 2 is a symplectic form on N, so it's not degenerate, then alpha is a contact form on P. Okay, and this is what is usually called a prequantization. So maybe, yes, S2N plus 1, right, is the prequantization of CPN. Okay. Okay, when you normalize the Fubini-Studi to give area 1 to the line at infinity. In fact, if instead you give area 2, right? So what you get here is RP2N plus 1 for the prequantization. Okay. Yeah, I think it's in this. Okay, so this is the prequantization. Now in N we have a Lagrangian barrier, or this case Lagrangian skeleton, right? This is gamma k. So gamma will always refer to Lagrangian things, objects, and these are on N. And so the claim, in fact, is that gamma k is 1 over k rational. And by this I mean that when you have M, as I told you, you have this gamma k. There might be so gamma k may have cycles, but if if it bonds a disk, so if you have a disk with boundary in gamma k, then the area of this disk is always a multiple of 1 over k. Okay. Okay, so this is one property of Bjorn's, of the case Bjorn skeleton, right? And now, so we're in this situation where we have gamma k inside this N, and then we will lift it to P, right? So we can lift it, so N, so we have N here, P, which is a fiber bundle. We have a connection. We have here in N, I hope you can see, yeah, I think you can see what I'm drawing. So we have gamma k, and so what we do is choose in the, sorry. So above one point, we take a fiber, take 1 point in the fiber, and then what we can do is just lift passes by parallel transporting them. Okay. And okay, usually when you do it, you have problems because these lifts, right? The point so above this point, I get this point here in the lift. So usually this lift depends on the arc, but because because this lambda k is isotropic, then you can see that you can show that there is no monodromy. So by this I mean that if you have a small, in fact, a small loop, right, you get back to y0 here. So it implies that this isotropic lift, so the force that you lift an isotropic thing gives you some Legendrian object. A Legendrian object in P. Then there is no monodromy, so it's locally embedded, but still you can have holonomy, right? So when you parallel transport along a loop in gamma k, but which is not contractible in gamma k, what you may do is get to another point here. And now the rationality observation shows that in fact here, so all these points are distant in the S1 fiber by 1 over k. So okay, S1 has size is a circle of length 1, and so basically between 2 points of the, so each time you parallel transport along a loop, a closed loop in gamma k, you will get back to another point in the same fiber, but which is exactly at distance 1 over k here. And so this implies that in fact this isotropic lift is not too bad. I mean, it's, if the rationality assumption will not have hold, right, then if you, so let's say a minimal Legendrian lift to be the lift above all the arcs, all the possible arcs in gamma k that start from y0, x0, y0, right? And all the loops or all the possible arcs, right? And okay, without this rationality assumption, it could have been, for instance, dense in the S1 in each fiber, right? So giving something very complicated. It's not the case, right? Its trace inside each fiber is in fact exactly k equidistributed points. Okay, so this isotropically lift lambda k is composed of exactly k equidistributed points in each S1 fiber over each point of gamma k. Okay, and now I'm ready to state the theorem. So in fact, this lambda k will be a Legendrian barrier at scale 1 over k. Okay, so the theorem is the following. So we are in the previous setting, right? So you have P of n tau, the prequantization, lambda k, as I discussed just before. And now, okay, you take lambda, which is any Legendrian submanifold. So let me check. Yeah, okay. And lambda any Legendrian submanifold of P, okay, of this prequantization. So it's an embedded Legendrian submanifold. Then I claim that for any, whatever the contact form that you consider, provided it is bounded by alpha, right? And less than alpha means that alpha prime is f alpha with f less than 1, but positive, sorry. Yeah, okay. Okay, whatever. Then for all these possible alpha prime, either lambda has an alpha prime Reeb chord of length 1 over k, or an alpha prime Reeb chord to lambda k of length 1 over k. Okay, so let me make this picture. So we have P. We have lambda k. So this is lambda k. And again, it is rather explicit in this setting because it's the lift of Lagrangian skeleton, and sometimes the skeleton we know the skeleton. Okay, so we have this lambda k, and now you consider any Legendrian submanifold lambda, and the claim is that either you have a short Reeb chord of lambda, or you have a short Reeb chord from lambda to lambda k. And this holds for all alpha prime, right? These Reeb chords are, so here this is the alpha prime Reeb vector field. Okay. So you see, I told you already that if I want to express things in terms of lengths of Reeb vector fields, I need some normalization. So here normalization is this one, right? Alpha prime is less than alpha, and alpha is fixed, right? Alpha is the one that I imposed at the beginning. Okay. So now maybe I will comment a bit on this result. This is the only result, right, in this talk. So let me comment a little bit. So I don't know much about contact topology. The kind of results that I may know are of the following kind for Reeb chords. So you have result a la given tal, right? That tells you, for instance, that when you are in RP2n plus 1, right, there is a reference Legendrian submanifold such that whatever lambda, another Legendrian, okay, every lambda will be Legendrian, every L will be Lagrangian, and gamma also will be Lagrangian. Okay, so you take any other, so you have a reference Legendrian in RP2n plus 1, such that for every Legendrian, there is a Reeb chord to RPN. Okay, and this is for any whatever alpha. This is interesting when you take for any alpha prime. Okay. So alpha prime Reeb chord. Okay, so this is one kind of rigidity statement concerning Reeb chords. Another one, let's say a la Monkey, but okay, I'm sorry for the references. There are many people who worked on this, but here you just take, so for instance, sorry, S2n plus 1, and the Legendrian in it, and then you always have a self-Reeb chord, and say here for alpha, an alpha Reeb chord of length bounded by something, 1 or whatever. Okay, so you see this statement here is an in-between, right? So on one hand, we have some reference Legendrian lambda k, okay? And then given another Legendrian lambda, it either has a Reeb chord to lambda k or to itself. Okay. The difference here is that we can bound the length of this Reeb chord. Okay, you have either one which is small here, or another one here which is small. Okay. So this is one thing that I wanted to say. Another one is concerning this. Maybe it looks strange, so maybe we wouldn't like to have. We might prefer to have, for instance, saying that lambda would have a Reeb chord to lambda k, and lambda, and for any lambda, and say lambda k is large. So when lambda k is large, this size should be 1 over k. Say once you fix alpha. And okay, so what I mean is that maybe I don't know if I've been clear, but maybe you could, you don't expect, but maybe you could hope, after only reading this statement first, that you could get only this kind of given tel, only get the given tel. Sorry, so I told you that you have here you have a result in between that tells you either you have given tel, or so it's a kind of you have two options, and you can't tell which one is the correct one. So you may wish to be able to say that the correct option is the given tals, right? And this I want just to explain quickly that you cannot hope for something like this, right? Because in fact, okay, saying that lambda so has no has no Reeb chord to lambda k of length 1 over k is equivalent to saying that lambda does not intersect the 1 over k sweep of lambda k by the Reeb flow, right? So let me write it. This is the same as saying that lambda does not intersect the 1 over k sweep of lambda k, okay, by R alpha prime. And this thing, once you fix k, right, this thing is something which is so this has dimension n. So this thing is of dimension n plus 1. Okay, maybe this is very complicated and it's very dense in the somehow, but anyway, this sweep has dimension n plus 1, right? And therefore you have points in the complement, obviously in the complement of this sweep. And now in the same way as okay, and now you very locally near these points you have small Legendrian. Okay, very small Legendrian localized near this point in the complement of this sweep. And if this lambda is very localized here, then it will not intersect so the 1 over k sweep of lambda k, and therefore it has no Reeb chord to lambda k of length 1 over k. Okay, but the point is that therefore this one will be in the first alternative, right? And this is well known that if you take a Legendrian which is very localized, then it has short Reeb chords. Okay. Okay, I think that's the only thing I wanted to state. Is everything fine? Is the statement clear? And maybe it's the point for a question if you wish. Yeah, Dylan? No. Okay, sorry.
So in the given tal result in RP 2n plus 1, how is it different? I mean, you said that there you have like bound on every Legendrian, you should have like a Reeb chord to RPN.
Yes. So the point, yeah, sure. But precisely in this given tile, you see, you have no bound on the length of the Reeb chord. Okay, so when you flow along, when you flow you RP2n+1 along, what am I saying? Yeah. No. Wait. You're right. So I thought that. So wait, what is the Reeb flow? So it's also this S1 bundle over. Okay, so maybe this given tile result is not correct, or what I said is not correct. No, okay. Okay, maybe I just don't know here. Maybe someone knows in the audience and can answer. So the question is whether it's true that any Legendrian has a Reeb chord to R. No, but okay, to RPN. No, maybe it's I'm sorry, maybe I just completely I said something completely wrong with respect to given time. It's funny. Yeah, okay. So maybe let me skip and after the talk I will check on given tell's paper. Okay, maybe it's stupid. What I said was stupid. However, the statement here is correct. The statement of the theorem is it's kind of strange. Okay. Yeah, I'm sorry. Another question? Oh, okay. Yeah, okay. Let's think about this afterward. So, okay. So let me continue, and I'll think later. Okay. So you see, this theorem, in fact, ultimately relies on a Lagrangian rigidity in the kind of Birans, right? So the one that I told you that a Lagrangian in the complement of a Lagrangian skeleton always has a disk of small area. Okay. Now this might be interesting to notice. I don't know. So yeah, the following corollary that so now this Legendrian statement has a corollary for Lagrangian immersion, and that in fact so Felix, I cannot get it right in Biran's proof. I don't know how to get this corollary without this Legendrian theorem. So, but maybe one can be smarter than me. So here, the statement is the following: you take n tau, which has to be simply connected for some reason. I don't want to get into it. Then if you have a rational Lagrangian immersion in n minus gamma k, which has only transverse self-intersection, then it has a symplectic disk with boundary on L of small area, of area 1 over k. And this means that that the rational constant for the 1/p is less than 1/k. Okay, and let me explain this. It's okay. So here you have n tau. Here you have p, and you have this this gamma k. Okay, and now you take Lagrangian immersion here in the complement of gamma k. Then okay, when you lift it in the same way as before, right? As I explained, what you get is a Legendrian here. Okay, in the complement, obviously in the complement of lambda k, because lambda k is a subset of the preimage of gamma k, of the fibers above gamma k. So here you have a lift which has no, sorry. So the lift of L is lambda here. And first, the Lagrangian immersion, so sorry, not the immersion condition, the self-intersection condition implies that in fact here it will be embedded. And also the fact that the Lagrangian immersion is rational implies that again here when you lift it to a Legendrian embedding of a closed manifold, right? And here the distance in the fiber is 1/p. And now if you use this theorem with alpha prime is equal to alpha, right? So the alpha Reeb vector field is just the S1 flow, I mean the translation in the S1 direction, right? So here you see that it has no, so there is no Reeb chord to this part, so to lambda k. So it has to have a short Reeb chord. So here 1/k Reeb chord to itself. But then it means that 1/p is has to be less than 1/k. Okay. Okay. So I don't know. Maybe someone knows how to get such a statement. I tried to get this statement directly, but okay, I couldn't. So maybe let me give a final remark. So the final remark is that this theorem holds also for, instead of, so here I've stated it for Reeb vector field, right? And it holds if you replace this Reeb dynamics by any Hamiltonian dynamics, provided that the Hamiltonian you consider, so time-dependent Hamiltonian you consider, is more than one. So it's a positive isotopy. So you take any positive contact isotopy, and this positivity has to be somehow quantitative, right? Then you have the same statement with alpha prime Reeb chord by replaced by the Hamiltonian Hamiltonian chord. Okay, so I think I'm good for this part. Okay, so in the time that remains, so maybe it's only a quarter of an hour, I will try to explain the strategy of proof. Okay, and okay, so first you have to should I say it or not? Yes, maybe. So let me be quick to explain how Biran Lagrangian barriers are proved to be barriers, right? So in this context that I explained, right, you have you have m omega. So you have m omega, and then you have this fiber bundle with Chern class omega. Yes, omega, and you take this connection form of curvature minus omega, right, alpha. You can also tensorize them. So take powers. You also have alpha k. You have a connection one form with curvature minus k omega. All right. And now, okay. And now what happens is that here, if you add now, sorry. So now, since you have a Hermitian bundle, you have a complex structure on the fiber. So when you add this complex structure, almost complex structure on M, right, compatible with omega, the point is that so the connection or the covariant derivative gives you a way to define nabla S. So it's a kind of, right? And this nabla S is a one form with value in the fiber, which is holomorphic, which has holomorphic structure, right? It's a complex line. So what you can do with J is you can, so here you have a vector and you have also J times V. So now on this nabla, you can compare the action of nabla on JV and the one on V compared with the multiplication by I in the fiber. Okay. And when you do this, so you can define holomorphic sections, the ones that sense nabla of GVS is equal to I nabla V of S, or quasi-holomorphic, meaning that the 1-0 part of the derivative, of the covariant derivative, is large compared to the 0-1 class, 0-1 part. Okay. So you have here this notion of quasi-holomorphicity, and then once you have done this, so this is here. This is Giroux, right? This is what Giroux noticed, that if you impose this condition, first you have such quasi-holomorphic sections, and then the vanishing set of SK is a symplectic hypersurface. Poincare dual to K omega is not very important here, but on the complement. So now you have M, and you have this sigma K. Okay, so this is the vanishing section of SK is equal to 0. And on the complement, there is Liouville form and a Liouville vector field. And this Liouville vector field splits the manifold in two. This is Biran decomposition theorem, all right? So first, the points that are attracted by sigma K, so that finish to their course under the Liouville vector field in sigma K, and the other ones, the ones that never are built to lambda K, right? To sigma K, sorry. And this is what I called gamma K, okay? And this precisely is the skeleton. Okay, this is the K skeleton. And so you have this decomposition, and now Biran's theorem is that, so let me call B the basin of attraction of sigma K under the flow, right? So it's the complement of gamma K. And this B, in fact, has very small capacities. Okay, so this is Biran theorem that the capacity of B, of BK, is 1/k. Okay. So whatever capacity you say CB or CLAG. Okay, and so this gamma k is this isotropic skeleton. Now, let me get to the Legendrian results and to explain at least the strategy of the proof. So we are in this setting, right? So we have N, which is integral symplectic manifold, and gamma k, it's a skeleton, P the prequantization, lambda k the lift, okay? And so here, so let me draw the picture like this. So I have N, I have P, okay, and I have gamma k. Okay, this is lambda k, this is gamma k, and I have something here in the complement. I have lambda like this, okay, and okay, you have lambda. This is Legendrian manifold, and you have a Hamiltonian contact function which is larger than 1, and you assume, so first, when you have such a positive function, the sweep of lambda under the isotopy, the Hamiltonian isotopy, is always locally embedded. This is because it's positive thing. And then, so it's locally embedded. And then you assume that it is embedded until time t, okay? And this exactly means that there is no Hamiltonian chord of size. So you assume that there is no Hamiltonian chord, no Ham chord of length more than, of length less than t, okay, for lambda. And now you also assume that the sweep belongs to p minus lambda k, right? And this means that that there is no Hamiltonian chord to lambda k, so no Hamiltonian chord from lambda to lambda k of size less than t. And so our goal is to show that t is less than 1/k necessarily, right? And so, for instance, here maybe it's okay. Let me do at least. Let me explain at least this. In fact, if you take h is equal to 1, so the contact Hamiltonian constant Hamiltonian 1, then right so did I say it already? I think no. Okay. Then the Hamiltonian flow is just the alpha Reeb flow. Okay. Alpha, where alpha is the standard one, right? So in fact, the dynamics in S1 is the one generated by h is equal to 1. So you see, if t was larger than 1/k, right? Again, saying, so this assumption, the fact that the sweep lies in the complement of lambda k is the same as saying that lambda belongs to the complement of the 1/k sweep of lambda k, and therefore that lambda lies in the complement of these full fibers, and therefore that when you project lambda down, so lambda down to n, here lambda lies in the complement of gamma k itself. And therefore, for instance, if lambda is embedded, has the good idea to be embedded, then you can use this Biran, so this Lagrangian rigidity, right? Now, when you are not in this case, right? So even in autonomous situation, right? It's another Reeb flow. So now the dynamic is not anymore the dynamic in the S1. So dynamic just flows this way, and it's more complicated, right? So you cannot argue this way, and you have to find another way of arguing. And I have 2 more minutes, so let me try to just give a short idea. So so let me think at what I need to say. Yes, so you have here you have P. Okay, which is this S1 bundle here. And you have again lambda K, something like this. Okay, and here is gamma K or whatever. And well, not really, but anyway. So in fact, the first, and then you have lambda in the complement, and you have an H sweep. Now, the first thing is to use Monkey's trick to lift this sweep to the symplectization of the prequantization. Okay, so here you have this symplectization, and this gives you something. So this gives you a Lagrangian embedding. So Monkey's trick gives you a Lagrangian embedding with area class in TZ. So the T being the length of the sweep, right? The fact that H is more than 1 gives you that, in fact, this embedding is in the negative part of the symplectization. So is okay. And the fact that the sweep does not meet lambda K, right, implies that it lies in the complement of it lies in the complement of R cross lambda K. Okay, so here you have R cross lambda K, and you have this now this Lagrangian in the complement with area class range in TZ. Okay, and so now basically what you want to do is to say that R, that in fact, so the statement is that R minus R cross lambda K is the skeleton, is the case skeleton of a polarization of S minus P. Okay, and then your Lagrangian here will have by this estimate on the area of the disk with boundary on the complement of K skeleton. So this Lagrangian will have a small disk, a short disk, sorry, and a disk of small area, and you're done. Okay, disk. So then the area class of L belongs to is 1 over KZ. What am I saying? Oh, okay, whatever. Yes, so I'm late for. So just one more word, just to explain the difficulty, right? So the point is that this is sorry. So what I've explained is this argument, right? You have to understand that you are a K skeleton. That this. So the point is that S minus P, so that the symplectization or the negative symplectization is not a closed symplectic manifold at all, right? So you have to compactify it. So you have 2 difficulties, in fact. One, that this symplectization is not closed, so you have to compactify it in some way. Okay, so there are compactifications. on one hand. So they exist. On the second difficulty is that what you want is to provide a polarization of SPB whose skeleton is this one, okay, is the R cross lambda K. And computing a skeleton is usually complicated. Given a polarization, computing the skeleton is difficult. But imposing a skeleton is kind of usually hopeless, okay? And here I want to impose the skeleton. And this can only be done, so this is hopeless unless there is some algebraic miracle. And okay, so the algebraic miracle here occurs, but not if you use, you have to use a compactification of your symplectization, which is not completely standard, and in fact, which is not symplectic. You have to use a non-symplectic compactification of this thing. So this means that, in fact, you are looking for polarization on a non-symplectic manifold. So the point is that you have to go until R equal to 0. You have no choice. You have to compactify between R equal to 1 to R equal to 0. You cannot stop just before. This would not allow for the algebraic miracle. So you have to go until R equal to 0. But on R equal to 0, the symplectic, so R alpha just degenerates completely. So your compactification just fails to be a symplectic manifold. So you have to rework all the Biran decomposition in this framework, in this particular framework. Okay, so that's all. I'm sorry for taking more time than expected. So I'm done. Thank you for your attention.
Are there any questions?
I have a quick question. This trick, does it work for a non-autonomous Hamiltonian?
Yes. This trick is yes, works for non-autonomous.
I see.
As far as I could check. But yeah. It's not really a matter. Yeah, okay.
This is a trick where you flow by the Reeb flow, then you flow by the Liouville flow, then you flow back by the Reeb flow and build this sort of rectangle.
No, it's not. No, it's not. So this trick here is that, okay. Yeah. No, it's not like this. It's just that in the, let me think, how to say it quickly. So you just so you have lambda and you have this 0, 1, which is the time along which you flow in so you have this phi h of lambda, right? And now the point is that, so this lies in the so these things lies in P, right? Now you have a way to lift it to 0, 1 S here by putting H whatever. Okay, so when you leave this thing, it's of dimension. So this is of dimension n plus 1 plus 1. This is n plus 2. And this thing has dimension 2n plus 2. This is not Lagrangian, right? But inside this thing, you can compute the symplectic form. And what you find is that basically when you pull back, so here this embedding lies in P cross R, right? And when you pull back the symplectic form, what you find is just ds wedge dt here, if you start here for Legendrian. And so you have ds wedge dt, so what you take, and okay, so here you have t is the parameter for which you are, sorry, not this one, t is here. And this one is the size is from r is equal to 1 to r is equal to 0. So here will be r, okay? And just, in fact, this 0t cross 0, 1, this has area 1. So what you can do is find, it has area t, sorry. So you can find a curve that encloses area t. And then if you take gamma cross lambda, then this is your L.
Let me see. So can you just say quickly, what's the second 0, 1 factor? How does that work?
This, okay, so for this, okay, I mean, it's always the thing with this, so you have to find it with H, so it depends, so basically the formula is something like this. So do I have an conclusion? Yeah. Can I add just one moment? I will add ajouter une page. I cannot write. Okay, I don't know where I am. And now nothing just works. Okay, so yes, okay, I have this one. So basically, it's it's a formula. I'm sorry, it's nothing more than this. So here you have 0t, this is t, and here you have 0, 1, this is s, and you to x, t, and s, you associate it in this s minus m. You associate something like this, phi t h of x, and here 1 over h of ht of x. S over ht of x. Something like this. So I don't remember exactly, but just that you include this Hamilton, this conformal factor into the picture. I can check if you wish. For the precise formula. Precise formula is
that makes sense. Thank you.
Yeah, T over HS. Yeah, but okay, so this is this one. That's the correct one. Yes, that's the formula. So here, yeah, what I said is that here you check that psi star of R alpha is precisely, I don't remember, SDT or whatever, or TDS.
And do you get an obstruction to embedding of prequantization of balls, like the contact balls, into these domains?
Yes, but
In special cases.
Okay, so the point is that it's a bit subtle. Just if you want to say something which is correct and non-trivial, so for instance, what you can prove is that you cannot. Yes, so okay, I can say this. What you can prove, but maybe this is obvious, I don't know, is that there exists no okay. If you take A larger than 1 over K, right, and you take yeah, so what you would like would be that you don't have contact and embedding of BA cross S1 in the complement of P of lambda K in P. But in fact, it's okay. So this I don't know. Maybe it has no chance to hold. I don't know. What you can prove is the following: that if you here put the standard contact form, and you just push it to here, then it cannot. So this contact form does not extend. So what you get is that then C star alpha standard cannot be extended to alpha prime. So there exists no alpha prime whose restriction to the which is equal to C star alpha standard on the and such that alpha prime is less than alpha. So I think somehow it remains. I mean, I think it raises more questions than it solves. That this result, I think it's a nice remark, but you see, if you really want okay, my personal feeling is that if you really want to get from this contact rigidity in the usual sense, you have to say more, because so this assumption that it holds only for H for those Hamiltonian which are larger than 1, yeah, give you a restriction on the applications. I don't think it's an empty statement, but there is still work. That's my feeling.
Thanks.
Can you say in half a minute how you deal with this degeneracy of the symplectic form?
Yes, I can. In fact, it's yeah, it's not so complicated. I can say it. Without getting into the details, basically what you have is the following picture, right? You have this. So here you have, say, you have this compactification, this projective bundle, right? So it means that the fibers over SPB over N, okay? So here you have, so it means that the fibers are S2, okay? These fibers have area 1 over K. Now here you have N0, and okay, what you have is a closed two form, which is you have n infinity, and this two form is non-degenerate on SPB. So omega 0 is symplectic on SPB minus n infinity. All right, on n infinity it degenerates. So now in the sphere direction, it's really a good symplectic form, right? On the fiber, omega 0 restricted to the fiber is symplectic. And now, okay, basically what I told you is that what we find is now this is why I need to take the whole projective bundle. In fact, in this omega 0, if you projectivize like this, omega 0 remains integral, belongs to H2 with values in Z. Okay, and for this you really have, or sorry, is it okay? Whatever. Why did I say no? Sorry, it's S2 of 1 here. I'm sorry, it's S2 of 1. Okay, and it has integral. So now you have the same thing. You have this LK, okay, above this symplectic projective bundle, and again you have alpha K. Just its curvature is not symplectic anymore above n infinity. Okay, so now you will construct. So you have already some you have a section of above n0, which is n. Okay, so this one is n. You have a section of LK above n. And what you want to do is to extend it to a section. So what you prove is that you can, in fact, extend this sigma k to a section which is still J quasi-holomorphic. Okay? And whose, okay. And now the point is the following. So you have, so here we have this sigma k, say. So the vanishing set, so this is still Sk is equal to 0. The vanishing set of Sk gives you again a symplectic manifold, except maybe here. Okay, maybe here the intersection. So it, in fact, okay. In fact, sigma k does not intersect the infinity if you choose well the extension. Okay. And now what you have to prove is that you want Beran decomposition theorem to hold, and to say that every point is either attracted by sigma k or remains in your skeleton. Okay, and the skeleton you choose Sk kind of an algebraic extension so that the skeleton remains this gamma k tilde. And so now the magic thing is that for k larger than 2, I forgot to say. Then you have a bit of analysis to show that for k larger than 2, in fact, the Liouville vector field is not defined here. It's not defined at the section at infinity, but in fact, it points outwards this section at infinity. So any point has either to remain in an infinite time in this part, or to get to sigma k. And once you have this decomposition, then this so you have this decomposition in two parts, which is the skeleton, which is gamma k tilde, and the basin of attraction of sigma k with respect to lambda k. And now this basin of attraction is already Beran thing. This thing has small capacity.
Okay. Thank you.
So the main point is to understand that this that for lambda k, in fact, the Liouville vector field, which is not defined on n infinity, just never reaches n infinity. The point, the place where the symplectic structure degenerates.
Thank you.
Okay, so thank you, Emmanuel. Yes.
Thank you for listening.